Right. Hi, everyone. I think we can start to get rolling. By the time I'm done this introduction, maybe a few more people will trickle in. But in the meantime, we can get the show on the road, get you in and out between 2 and 3. We want to honor that for you guys. So just want to say welcome to everyone. Thank you for joining us today for this next installment in our research speaker series. My name is Annika Trimble, and I live in Inuvik, Northwest Territories. I'm the outreach coordinator for Aurora Research Institute. We also say ARI to keep it short. So it's really wonderful to see everybody signed up and here gathered from across the NWT and the rest of Canada. To begin, I want to acknowledge that we in Inuvik are on the traditional lands of the Gwich'in and the Inuvialuit peoples. We extend our deepest respect and appreciation for sharing this land with us. We further extend our respect to all First Nations, Inuit and Métis people of the North who call this territory home. So before we get started, I want to go over a few housekeeping items so everybody's aware how to participate in today's webinar. At any time during the webinar, you can go ahead and submit questions to the presenters. If you're using the Zoom app, you can hold your mouse over the bottom of the Zoom window and there's a control panel there and you can type your question into the Q&A at the bottom. The questions are only visible to the webinar moderators. And if you aren't in the app or you don't have that feature or can't find it, you can also drop your questions into the chat. We're going to save answering the questions for the very end. The presenters will go through as many as we can get to during the time that we have today, but I trust that we should be able to answer most of what you guys have or whatever comes up. Just to make sure everybody's aware, we're going to be recording this webinar, and that's so that anybody who has internet issues or maybe they couldn't make it today to today's talk, they can always watch the recording afterwards. All of our virtual speaker series talks are available to be viewed later at the ARI website. So I've put the link in the chat for now, but I'll do it again towards the end of the talk in case anybody joins us a little later. So today we are joined by 3 researchers, 3 NWT resident researchers. We have Alice Wilson, permafrost specialist, and she's one of ours. She's from the Aurora Research Institute and she lives here in Inuvik. We have Dr. Ashley Rudy, permafrost geohazard scientist. She's with the Northwest Territories Geological Survey out of Yellowknife. And then Tim Ensom, he is a PhD candidate with Wilfrid Laurier University, and he's been doing research in the North for many, many years. For a long time. So it's very good to have all 3 of you here to talk about what's happening with permafrost along this brand new roadway. So for those of you who might not be familiar with our region, the Inuvik-Tuktoyaktuk Highway that we're talking about today is only a few years old, but it's already had a really big impact on our region. It's connecting communities, it's bringing new people and resources and opportunities into the North. And it's also changing the way that we access the land. So understanding the state of the permafrost and the changes in that permafrost along the highway is really critical. So this presentation will provide a bit of an overview of the permafrost monitoring program that's taking place along the highway. We're going to see some preliminary results from a snow manipulation field experiment. And we'll get into some of the seasonal changes, the hydrothermal changes of streams that are near the highway and highway infrastructure. So I think it's going to be a great talk and we hope you enjoy the presentation. Again, if you have questions, drop them in the chat or the Q&A and we will get to them at the end. All right. Thanks, guys.
Yeah, thank you so much for that introduction, Annika. So I'm going to start us off on our presentation on developing a permafrost research program along the Inuvik-Tuktoyaktuk Highway, or as most of us more commonly refer to it as the ITH. And to provide some context and some background, because not everyone is familiar with permafrost, I'm going to give a little bit of a permafrost 101 to start us off. So what is permafrost? So permafrost is defined as ground that is at or below 0 degrees Celsius for 2 or more consecutive years. And it can consist of bedrock, soil, ice, organic material, or a combination of those. For Canada, almost half of Canada is underlain by permafrost, And the region we're in the Mackenzie Delta region, it's over 90% of our ground is underlain by permafrost. As long as you're outside of the Mackenzie Delta itself, and the Mackenzie Delta, it's more like 50 to 90% because of all the heat coming from the water. And if we look at it a different way, this figure shows the Arctic Ocean, so the north on the left, and as you head right, it goes further south until you hit high level Alberta. And it just shows how the extent of permafrost decreases with latitude. And what I would like to focus on is this region here near the tree line where Inuvik is. The mean annual air temperature is around -8, and we have continuous permafrost. And continuous permafrost can range from 100 to 400 meters thick, and really is underneath all of us. So what about the region that the ITH is going through? So there's quite a bit of environmental variability. This region has a glacial legacy. We were glaciated during the last glaciation, and as a result, there's a lot of buried glacial ice that's hidden within the ground. And we also have some ecoclimate gradients. So that means that there is quite a variation from where you head in Inuvik south of tree line to north of tree line as you head towards Tuck. And this variation does cause variations in permafrost temperatures. So in Inuvik, in the forested areas, permafrost temperatures range from -1 to -3 degrees Celsius, and above tree line towards Tuck, they're more like -4. And with these variations, it's also to understand there is a variation in ground ice, and I'll get more into different types of ground ice in a future slide. The region we are in, the Western Arctic, is one of the most rapidly warming regions, and because permafrost is very thermally defined, because it is defined by it being below 0 degrees Celsius, if we have warming temperatures, we are going to see changes to permafrost, such as the ice within the permafrost melting and thawing of the permafrost. And so if you see here, Inuvik is quite rapidly warming, and we're seeing an average of increase of 7 degrees Celsius for every 100 years. Another term that I will be using a few times is the active layer. So the active layer is this region above permafrost, and it thaws every summer and then refreezes every winter. So it's not permafrost because it is thawing and freezing all the time. And it is influenced by different factors, and will vary based on climate. You'll generally have thinner active layers as you head further north, but it also is influenced by vegetation and snow, as that will vary the ground surface. And why are we interested in the active layer? We're interested in the active layer because it acts as a buffer to the top of the permafrost. And the top of the permafrost, as you can see in this cross section, tends to be more ice rich, and you tend to have a lot of segregated ice in this area. As you can see here, the whitish gray is all ice towards the top of the permafrost. So if the active layer goes down and increases to that, you're going to have melting out of this ice and thawing permafrost. So there are several different types of ground ice, and they all vary, and they range from quite small to pore ice, and that's just ice that fits in between different pores, such as between the pores of sand and different types of soil. And it can range to quite large, so massive and glacial ice. And these can be tens of meters thick of almost pure ice. And here's a nice example of a core that is pure ice that was collected from permafrost. And so how does permafrost relate to subsidence? So if you have here, you have your active layer and you have ice-rich permafrost. If the active layer increases and starts to melt the ice that is located in permafrost, when that water and ice is removed from the system, the overlying material is going to subside down further into the ground. And that's when you have this uneven subsidence that can occur with permafrost thaw. And I think this is a common issue people often think of related to permafrost thaw. And it's an issue for infrastructure. As you can see here, this is an example from a road outside Yellowknife, but we often see it on the ATH. And it can be an issue for buildings where you have uneven subsidence. And it's difficult when you're trying to build something on an even surface. And so now, based on this quick little background, I'm going to now leave it to Ashley to discuss the Applied Permafrost Research Corridor.
Okay, great. Thanks. Thanks, Alice, for that great introduction to Permafrost 101. Yeah, so I'm going to talk a bit more broadly to the theme of this talk, which is the development of an applied permafrost research corridor for the Inuvik-Tuktoyaktuk Highway, so the ITH. So as Annika mentioned, the ITH is a gravel road built over challenging ice-rich permafrost terrain. The development of the roads provided unprecedented access to this dynamic permafrost environment, which has increased research interest and activities of scientists from across Canada and the world. So it's created a really unique opportunity to capitalize on the legacy of research and scientific infrastructure, and in turn, the region's become a hub for applied permafrost research. With an increasing interest in permafrost landscape change in the region, we need to be better at how we transfer and mobilize the knowledge that's being generated. In addition, due to the number of local organizations that are really active and engaged in permafrost research and permafrost-related interactions, there's a building capacity or increasing capacity. So again, an opportunity to build robust relationships as we continue to conduct research in this environment. Next slide, please. Yeah, so the development of applied permafrost research corridor has a number of focused objectives, including the collection of data to assess performance of infrastructure, to identify and monitor high-risk areas, to collect baseline research and monitoring at a number of sites, test innovation, different types of engineering techniques, and then to use all this information to learn for future applications and future infrastructure projects. So these objectives are derived with the understanding that there's a high value in pure research that also has an application. So essentially, fundamental science is foundational to adaptation. Next slide, please. So through the inception, planning, and development of the ITH, there was a significant amount of data collected that included geotechnical and thermal data sets. So geotechnical data is data that we get when we drill a hole in the ground or a borehole and extract that material. So the type of information we get is information about whether the subsurface is rock or sand or clay, whether there's ice, minimal ice, or even sometimes a lot, or as Alice mentioned, massive ice. And this geotechnical data is a really valuable look into subsurface conditions, which again can play a role in whether we're going to expect subsidence or permafrost degradation in the future. So there was about 88 holes drilled along the ITH between 2012 and 2017 along the alignment of the proposed highway, at stream crossings, along embankments, and at bridge pilings. And we were able, the Department of Infrastructure was able to repurpose a number of these sites to actually collect ground temperature data. So once you drill the hole, that's the hard part, you can install a plastic casing and then actually put a thermistor cable down the hole. So this is one type of ground temperature cable where there's a number of different sensors that are at various depths along the cable, and the sensors collect ground temperature data at whatever depth it is in the hole. This data then is stored in a logger, and then every year we go and download these loggers, ultimately developing a really robust ground temperature data set. So at about 60 of those 88 boreholes, ground temperature cables were installed. And we now have this really nice data set of thermal conditions that are associated with road conditions or disturbed terrain. Because once we build a road, we're disturbing it from its natural state. So in order to contrast disturbed ground temperature or thermal conditions, in 2017, the Geological Survey of Canada, as well as the Northwest Territories Geological Survey, or I'll refer to it as the NTGS, they installed an additional 12 boreholes at 4 different clusters of sites along the ITH. So these are boreholes that are about 100 to 200 or 200 to 500 meters off of the right-of-way and represent natural conditions. And so at each of these clusters, there are 3 boreholes that range in depth from 10 to 20 meters, and they are in, each of those 3 boreholes are in different terrain types. They're in peatland, hilltop, and riparian conditions. And Alice is going to talk a bit more to that with her snow manipulation experiment. So the NTGS has worked with the Department of Infrastructure, the Geological Survey of Canada, and the Aurora Research Institute to ensure that this network of loggers is maintained and downloaded annually, leading to this really substantial permafrost data set for the ITH. Next slide, please. So currently all the geotechnical and the ground temperature data up to about 2018 that's been collected along the ITH has been published as open reports through the NTGS. So these are accessible online where you can download the data as well as metadata on how the boreholes or the data was collected. And these data sets form the foundation for the Northwest Territories Permafrost Database. So this is a database that's in development where the goal will be to host all permafrost related data, both historic that we can get our hands on and all future ground temperature and geotechnical data, to have it all hosted in one spot. So the first phase is nearing completion, which was the development of the actual database structure. And we're in the process right now of uploading that data to the database. The second phase is the public accessible side, or the web portal. And this is going to be beginning shortly, and it'll allow community members, industry, other researchers to search for the data through a spatial view or through a map or through different keywords, and then to get access and download that data and the associated metadata. So the development of this NWT Permafrost database is important to support infrastructure planning and innovation in permafrost regions experiencing the effects of climate change, which in this area, or in the entire NWT, is one of those regions. It also allows or supports the provision of data to research partners and industry as well as communities to ensure that they're conducting data with as much data that's accessible for this environment or within this region. Next slide, please. So with the collection of all this data, we are able to use the corridor as a bit of an experiment. So we can start to use data that's been collected to evaluate the performance of different aspects of the road. So this is an example of where we've used embankment data to look at how well the embankment's performing. So the embankment, when the thickness in the embankment, or we build up the road off of the natural environment or natural landscape to hopefully ensure that we don't actually disturb the underlying terrains. We want to keep the natural landscape frozen. And so that's the purpose of the embankment. So at 14 locations along the ITH, temperature cables were installed horizontally across the embankment and then vertically through the embankment into the native soil, or into that, what would have been the original terrain. And so ultimately we would like that native soil to stay frozen and possibly actually aggregate or grow into the embankment, creating a nice buffer between the disturbed road surface and the natural landscape. Next slide, please. So what I have here is ground temperature data from those cables in the embankment. And so those are the green and the blue lines. And then I've pulled in data from those sentinel sites, so that natural landscape, and those are in the pink and the purple. And these sentinel sites are from approximately the same location along the highway as where the embankment temperature profiles are. So this is data from about 1 meter depth within the ground. So that's about the depth of the active layer, so where we have expected thaw, and is close to the embankment thickness in some locations across the highway. So on the x-axis, we have dates. So this is about 3 years of data from the summer of 2017 to last summer. And then on the y-axis, it's ground temperature. So right off the bat, we can see that there's a really large swing in the temperature profiles of the embankments. It gets really, really warm in the summer, and very, very cold in the winter. And this is a direct reflection of the properties of the embankment material. So it's crushed rock and gravels. It's also darker in color. So in the summertime, it heats up really fast. It absorbs a lot of that heat, leading us to get temperatures greater than 10 degrees. In the wintertime, because the road's plowed, the cold winter temperatures have a direct impact on the road surface, causing it to get very, very cold. If we look at the natural landscape, those sentinel sites, the pink and the purple, we see we have a much more dampened impact or effect of air temperatures on ground temperature. So we have this ground has remained permafrost, so it never reaches above 0 degrees in the summer, and then we see cooling in the winter. And the dampened impacts, or the dampened profiles, are a result of terrain conditions within the natural landscape. So in the winter, we get snow, which insulates the ground, keeping it buffering the impact of the cold winter air temperatures on the ground. And then in the summer, we have vegetation, again, causing a change in insulative properties. So what does this tell us about whether the embankment's performing as it should be? So at 1 meter depth, we see the embankment thawing completely through, likely into the underlying natural terrain. So at this point, from this data, it's not showing that we're having the development of a frozen core. However, if we look at this 3 years of data, we do see a downwards trend in mean annual ground temperatures. So it is cooling. So this is something to continue to monitor as we move forwards. And there's a university PhD student at the Carleton University who's using this embankment thermal data to look at embankment thermal regimes along the ITH and the Dempster. So it's a nice example of how this baseline data is being used for another research project, for an applied project. Next slide, please. So in addition to this network of ground temperature data sets and geotechnical data, we're also looking at mapping and monitoring hazards along and beyond the right of way. So these red dots are thaw slumps that are a type of permafrost landslide near the right of way along both the Dempster and the Inuvik-Tuktoyaktuk Highway. So at each of these features, we've installed ground temperature cables within the slump or the landslide, and then adjacent to it again in that undisturbed terrain to look at how ground thermal profiles change once you disturb the landscape. So there's one feature in particular that we've been monitoring more closely. It's the photo on the far left, and it's an example of a thaw slump that's approaching the Dempster Highway. Next slide. So it's this is the same feature, sorry, and it's approaching the Dempster Highway at kilometer 28.5. So it's just past Fort McPherson, towards the Yukon border. And so we're looking down towards the highway here. So you can see the highway in the background. And this is a type of permafrost landslide that stays active for a very long time. So it's not like a typical landslide you might think of where it occurs and then it stabilizes. These features occur where there's a lot of ice in the subsurface, and the occurrence or that formation, the prevalence of that ice leads these features to be quite active for a while. Next slide, please. So one way we monitor these features is through time-lapse cameras. So this is a time-lapse camera pointing upwards at the slump away from the road. And so Alice, can you point out where there's ground ice here? I can't see your thing. So there's ground ice. I'm not, oh yeah, perfect, thank you. So that gray kind of shiny smooth area is about 10 to 12 meters of ground ice. And so because there's all this ice exposed, as you can imagine, during the summer, we get a lot of melt. And then if you could play the video, if it will play. This worked when we went through it ahead of time, but maybe because you have the pointer on, can you press space? Does space play it?
Sorry, now it doesn't want to, let me, there we go.
Oh, perfect, thank you. Yeah, so we're looking upwards, and so this is time-lapse footage from this is actually cut down to about July to early September from 2019. And we can see as that ice melts, it creates this muddy slurry that builds up, and we can begin to see it start moving downslope. So the movement of this material downslope is what's of concern to infrastructure managers as this material is moving down towards the highway. So during this summer, it was a pretty active year, and the ice in the foreground actually grew all the way back. It melted all the way backwards into the upper head wall, now increasing the amount of ground ice upwards of 15 to 18 meters in that head wall. So next slide, please. So this is time-lapse footage looking downwards, downslope. And so we'll see the pulses of this material to the right of the screen as they move down towards the road. And so through our observations this summer, we discovered that there was 3 pulses of material, again, that started about the middle of July and kept moving until early September. And through monitoring of this over the number of years, we've been able to measure the distance that material reaches towards the highway. So in 2017, the material reached about 230 meters from the highway. And then last year, it reached about 500 meters from the highway. So the Department of Infrastructure is monitoring the site closely. A surveillance system has been installed to better understand how that material is moving, when it's moving, and how fast it's moving, so that they can ensure public safety of the highway at this location. Next slide, please. So this is a really unique region to work in. There's a lot of interest in permafrost landscape change. And so all three of them, whether that's Inuvialuit Land Administration, environmental monitors, or wildlife monitors from the HTC and RRCs. And over the last 3 years, we've had the opportunity to collaborate with the ILA on the development of a permafrost monitoring initiative, where we're working together to develop templates and tools for monitoring and archiving permafrost and permafrost infrastructure related observations. So we had a recent workshop this past June, which also included members from Imariuk and Manaxi, the community monitoring programs that are coordinated through the Fisheries Joint Management Committee, as well as Tuktoyaktuk Community Climate Change Resilience Program members. So it was a really amazing opportunity to share knowledge with these groups who have such extensive knowledge of the land, the landscapes, and how it's changing. And as we continue working in this environment or this region, we really look forward to growing these relationships and continuing to share knowledge and help build capacity surrounding permafrost landscape change where needed. Next slide, please. So ultimately, the development of an NWT permafrost research corridor is really valuable in this environment, as it's a dynamic permafrost landscape that we're seeing a lot of changes. Through working together, we're able to develop a collective and focused research vision. Again, able to capitalize on the scientific legacy and the logistical investment that's been in this region for years, not only from researchers, but with ARI being located in Inuvik, there is a lot of capacity to do research. And again, there's just so much interest. So there's an immediate interest in the results of the research and the development of a monitoring program for this region. So continued development of this research corridor will help contribute to northern governance, scientific leadership, and coordination. And because we have these monitoring sites and this baseline data, it allows others to do applied permafrost research, which is something that both Alice and Tim are going to speak to in the next couple of slides. So with that, thank you.
Okay, so I'm going to be talking about the snow manipulation experiment that I'm taking a lead on. Oh, something has happened and I can't go to the next slide. Okay, there we go. So to provide a little background again, we know we have permafrost underlying this entire region, and we have the active layer on top. And what's going to influence permafrost and the active layer are surface conditions and the climate. So if you have different vegetation, it has different abilities to reflect either the sun or shade the ground, which can help reduce the amount of heat entering into the system in summer. But it also changed the way that snow gets trapped. So if you have more shrubby or forested areas, you're going to have increases in the amount of snow being trapped because there's less wind to pull it away, such as north of the tree line where you see hard-packed, scoured landscapes. And the way the snow works is, think of it as a giant blanket, because if it's less dense and it's thicker, it's like a giant duvet and blanket for the ground. So all that heat that entered the system in the summer can't as effectively escape in the winter. And so if that happens and you have increases in snow throughout time, what's going to eventually occur is you're going to have more heat trapped in the system, and in the following summer, when more heat gets entered in, you can result in increases in active layer, as well as thawing of permafrost and potentially subsidence and other issues associated with thawing of permafrost. So the importance of snow is it's important to have a better understanding of it. And so how does that impact when you alter the landscape? How is that going to have an impact? So as Ashley had kind of shown you before, if you have a highway added, this is a cross section. So here is the top where you'd be driving. You're creating a new surface. So what we want to see is an increase of the permafrost into the road. And that way you're not going to be influencing the original substrate, but you're also changing the topography. So that's going to have an influence on the amount of snow, because you're going to have areas where it can be more easily trapped. And by increasing snow, you could have potential issues of active layer increase and heat entering into the system and potentially having a negative impact on the permafrost. So degradation of permafrost can lead to settlements of embankments and surrounding terrain, and this can happen in any kind of developed environment where you're changing the surface. So there's two main objectives to the snow manipulation experiment. One is to get a better understanding of the relationship between snow cover and surface temperatures, and to be able to have a more quantitative values associated with it, and to determine whether snow manipulation could be a viable method for decreasing permafrost temperatures, such as along road embankments or other areas where we're seeing higher risk of permafrost degradation. So I have 6 study sites where we are doing some snow manipulation. On this map on the left, you can see the Inuvik-Tuktoyaktuk Highway sneaking its way up to Tuk, and the labeled locations are where my sites are. Now, these all are paired with the Sentinel sites Ashley mentioned before, where they have 10 or 20 meter cables installed, and I have set up sites right next to them. The reason for this being that I already have, with the Sentinel sites, several years of data. It should be an undisturbed environment, but it also provides me with several different types of environments I can compare. And there's 2 main factors I can compare. One is that we have 3 sites above tree line. So those are the ones located in Trail Valley and at a pit, and 3 sites below tree line. And for each site above and below tree line, I can compare upland hilltop sites, peatlands, and disturbed environments. And my disturbed environments are source pits where they used gravel, where they got gravel to build the ITH. And we're now seeing permafrost degradation. So at each of these 6 sites, I am monitoring the snow manipulation. So how do I do that? So the first thing we do is we determine the location of the sites, and then we've installed several temperature cables. Now, I don't have the ability to install a 10 or 20 meter cable, so using this portable talon system, at each site, 3 3-meter cables, the same kind Ashley has shown previously, were installed in the ground to 3 meters depth, and they can be used to compare those temperature data to the control sites. Those were installed in the summer of 2019 and have been continuously collecting data ever since, and I download them once a year. And then for the winter, we do the compactions. So the snow compactions, we have a 50 by 50 meter area that encompasses all of my temperature loggers. So I have the ones at 2 meters depth and several surface loggers to be able to account for any variability in terrain. We use a snowcat to compact it. And this is done 3 times a year, once in December, once in late January, and then again in March. And associated with each of those compactions, there's a lot of collection of snow data. So a lot of snow depths are collected before and after compactions, as well as snow densities. And now what snow density tells us is how much snow there is per certain area. And the way that's calculated is we use this tube here, we push it into the ground, see how much snow we have in a known volume, and you can weigh it. And the reason this is an important thing to know is because the more dense the snow is, the more easily heat can escape out. So the idea behind the project is by decreasing the amount of snow, can we more effectively help permafrost decrease temperatures by losing heat throughout the winter and stabilizing it further. And just to illustrate what it looks like after it's been compacted, here's one of my Inuvik peatland sites. There's one of my field assistants, Ryan, for scale, and this is at the Inuvik peatland site just north of Inuvik. And so just some preliminary results. On this figure on the left, I'm just going to show you results from the two pit sites, as they are the most distinctly different, being furthest apart north and south, but also have very different snow characteristics. These sites close to Tuck have very little snow. So doing the compactions, results show that once you have less than 20 centimeters of snow, it doesn't really make much of a difference compacting it. But at all sites that had an average of more than 20 centimeters of snow, we did have a significant decrease in snow depths after manipulating. And these were all measurements from March. There had already been 2 compactions completed before these ones. So there is a significant change associated with this decrease in snow depth. We did have an increase in that density. So there should be more heat able to escape out after the snow is compacted. So did it work? So here we have a graph. The 2 lines at the top, those are the sites near Inuvik. So pit I-418, it's the first pit as you head north out of Inuvik. And then the purple and blue lines are pit 177, the one closest to Tuck. So the site that had very little snow, the temperatures do decrease quite effectively, but there is not much of a difference, and you can't see a real impact related to the compaction. However, this red line here is the compacted site. And if it wasn't compacted, you wouldn't see the temperatures go much below 0. So we are seeing a response to snow compaction at sites that have greater snow cover. And so next steps is I have another year of data to collect, and we've done 2 years of snow surveys and compactions, and trying to use this data and working with some grad students to try to model it to see if we can better understand how each of these different environments are responding to changes in snow cover, and see if this can be effectively applied elsewhere. Okay, and that's all for me. And now I'm gonna leave it off to Tim to discuss thermal regimes and streams.
Thanks very much, Alice and Ashley. And to continue on our topic of permafrost research along infrastructure corridors, I'm going to be speaking about the temperatures of streams in this part of the Western Arctic and how streams represent a distinct permafrost environment. In the title here, thermal regime means temperature conditions. Next slide, please. As Annika mentioned, I live in Yellowknife, and I'm collaborating with the Northwest Territories Geological Survey, ARI, and a few other partners as a PhD student with Wilfrid Laurier University. I introduced this project a few years ago at the ARI Speaker Series in 2018. Next slide, please. As the climate warms, we need to understand current permafrost conditions in the different types of terrain in this region in order to make informed projections about how permafrost will change. Streams are very common on the landscape here, and they occur in many different environments in the Beaufort Delta area. Knowledge about stream conditions and how they might change is important for communities, transportation infrastructure, and land use. Next slide, please. Another reason for examining streams is to learn more about winter stream flow, which might increase as the climate warms. We know that large rivers in the Western Arctic can flow all winter, and the early 1980s photo here from the northern Mackenzie River provides good evidence of sustained winter runoff in a small river at its outlet. Next slide, please. We don't know nearly as much, though, about winter water movement in smaller streams or riparian corridors. This photo shows an overflow event about 40 kilometers south of Tuck, observed when the air temperature was minus 30 degrees Celsius. The catchment, which is the contributing area for this overflow site, is only about 3 square kilometers, which is really small. Next slide, please. Streams that have winter flow can represent safety and management challenges for infrastructure, like highways, if flow lasts for long enough in the winter to freeze and block culverts, like at this site at the ITH. The trapping or impoundment of spring freshet by blocked culverts can lead to embankment scour or even washout, like we see here. Next slide, please. These observations and the knowledge gaps have led to the research questions here. We're especially interested in the winter thermal regime of streams and also in the causes of variability in stream temperature over time, and also variability between different ecological environments and between streams of different size. Next slide, please. In this region, we have the benefit of a legacy of environmental research in permafrost, including thermal investigations of streams at the sites shown here on the map. These projects were done mainly to describe the environment and the permafrost of the Mackenzie Delta area and to inform the planning and operation of the Dempster Highway, the ITH, and the Mackenzie Gas Project. Next slide, please. Ashley has described the more recent temperature monitoring sites, particularly between Inuvik and Tuk. These sites are routinely published, as she said, and interpreted by the Northwest Territories Geological Survey and partners, and will be incorporated into the Northwest Territories database. These data sets can help us understand a variety of environments, including streams. Next slide, please. We'll take a look first at the thermal regime of a small tundra stream. This is the west-facing view from the ITH at kilometer 103, about 40 kilometers south of Tuk. The stream is indicated by the blue line. By this date, in the late winter of 2019, there was about half a meter of ice in the channel and just over a meter of wind-blown snow on top, hiding the stream and making the landscape look flat. Next slide, please. This figure shows the temperature of the stream and a nearby hilltop surface between summer 2017 and fall 2020. The stream bed is shown in solid blue, and the temperature of the ground surface in the riparian margin beside the stream is in green. The ground surface at the hilltop is shown in dark red, and the very light blue line is air temperature. We can see that in the first 2 winters, the stream system remained at about 0 degrees and was much warmer than the upland terrain. This suggests that there is moving water in the stream throughout the winter, despite the surrounding land being really cold and the presence of thick permafrost. Winter 2020 was especially cold, with a whole lot less insulating snow than normal in this part of the region, and in that winter, the stream bed froze. The figure shows that the thermal regime of the upland landscape is more predictable from one year to the next, but that the temperatures of small streams on tundra could be much more variable from one year to the next. This is important because small streams like this represent a substantial portion of the landscape. Next slide, please. Data also suggests that streams in the taiga forest might have more consistent temperatures from one year to the next than tundra streams. Average stream bed and riparian surface temperatures in a taiga environment, shown in the photo on the left, were only half a degree to 1 degree colder in a low snow year than their average over the previous 2 years. In a tundra stream like the one on the right, average annual surface temperatures were 3.5 to 4.5 degrees colder in the low snow year than their average for the previous 2 years. Stream snow cover has been observed to be thinner in taiga forest than on tundra, and this may occur because a thicker tree canopy covers streams in the forest, and the forest may also block the wind, so less snow is blown into taiga streams, whether or not there is lots of snow in the surrounding forest. Snow can more likely accumulate in tundra streams if there is snow on the surrounding land. Next slide, please. The size of the contributing watershed, or the catchment, is another important influence on surface temperatures in riparian environments and stream beds. The figure here shows temperature on the vertical axis, with average temperature shown as points and temperature range shown as lines. Each point and its lines represent the temperature record from one of the streams shown in the earlier map for up to 3 years during the past decade. The horizontal axis is catchment area and is logarithmic because of how much bigger some of these watersheds are than others. The largest watershed is Campbell Creek, near its outlet the largest stream is Campbell Creek, near its outlet into the East Channel, south of Inuvik. And the smallest stream is the outlet of Big Bear Lake near Trail Valley Creek Research Station. Minimum annual winter temperatures increase with catchment size, and these minimums range from about minus 30 degrees Celsius in the smallest stream to unfrozen in the largest streams. These data show how the smaller streams refreeze in winter, while the larger ones tend not to freeze. Next slide, please. Talix are parts of the ground that are always above 0 degrees Celsius, unlike permafrost or seasonally frozen ground. Talix are common under big lakes, and stream temperature data so far suggest that talix also occur under streams that have catchments more than 140 square kilometers or so. There may be smaller talix under streams that we can more likely identify with geophysical surveys than with thermistor sensors, which have to be really carefully placed. This figure shows the thermal condition of the thermistors attached to the deep Hands Creek bridge pilings between summer 2017 and fall 2020. Hands Creek has a wide floodplain, and really coarse glacial fluvial material makes up the Hands Creek bed. So water and therefore heat can move through this material. Heat advection is what we call the movement of heat in moving water. Thermistors continuously below 0 degrees in the figure here are shown in purple when they indicate permafrost, and those in blue are seasonally below 0 degrees Celsius. Thermistors that are shown in orange have been above 0 since monitoring began over 3 years ago and indicate part of the talic under this stream. Next slide, please. Off-ice, sometimes called icings, can occur naturally or be caused by human disturbances to the thermal regime of streams in cold regions. The growth and distribution of off-ice can tell us about the timing and the amount of winter flow in streams, which can often be difficult to observe otherwise beneath snow and ice in the winter. Highway crossings can cause streams to cool and freeze to their beds really fast in the early winter. If runoff is still occurring in the stream, this blockage can force water to the surface and result in the accumulation of off-ice one layer at a time. On the left in this slide are 2 icings observed 40 to 50 kilometers southwest of Tuck, and the photo on the right is the annually recurring off-ice body mainly on the upstream side of the bridge at ITH kilometer 8. The growth of this off-ice is also shown in the next slide. However, most winter hydrology results for this project will be left for a future presentation. Next slide, please, Alice. So this is a video made up of daily photos at 1 p.m. In the creek at kilometer 8 from fall 2018 through to spring 2019. We're mid-December now. You can see the ice accumulating. We're now in mid-February and mid-March now. This is about a typical size of icing over the past half decade at this bridge. In some cases, as many of you know, the ice can almost reach or even contact the bridge span. Next slide, please. Just to wrap up, stream environments in continuous permafrost can have distinctive thermal regimes from nearby upland terrain, and understanding this regime is important for projecting future changes in permafrost and hydrology. Catchment size, ecological setting, and snow cover are important controls too on stream thermal regime. This is really important for understanding natural environments, but also for understanding the interactions between infrastructure and streams in permafrost landscapes. Next slide, please. We're really lucky to have the support from a number of funding organizations and other partners, and we look forward to continued work together. We really appreciate your attending today and for your attention, and also ARI's work in making this possible. I'll turn the program back over to Annika, and we look forward to talking about your questions.
Wonderful. Okay. Awesome. So our panelists, just thank you guys so much. It's really great to hear what's going on. Thank you all. We can keep our videos on for the Q&A session. We have a couple questions already. Just a reminder, we'll do some questions. If people have to break off at 3, you can always watch the rest of it at our webpage, nwtresearch.com/outreach/speaker-series. That's in the chat there. And in a day or two, that should be posted there. So our first question comes from Elzbieta. It says, hello all, great presentations, thank you. Alice, what is the depth of snow for maximum insulation? How much do you compact snow for the least insulation to occur?
Okay, so as for the maximum depth, I don't have a concrete value. We don't actually, ironically, the 2 winters we've done the project so far have been low snow years for Inuvik, so it'd be nice to do another year to have an average snow year. But we haven't had enough snow here to very effectively insulate, but we still see the impacts of the snow insulating the ground. But when it comes to the compaction, we are only able to get the compaction that the snowcat offers us. So that's why I do the snow depths and snow densities before and after each compaction. But looking at the first year of data, I haven't been able to dig down into the second winter. Generally, it reduces the snow depth to about half at the deeper sites. And at the deeper sites, it also has almost doubled the snow density. So it is quite effective, and it would be interesting to look into different methods of compacting, but it's the snowcat's an effective way that we can do it with a more or less smaller, lighter, large vehicle. And that would be possibly used by industry if it were to be applied somewhere else, unlike a snowmobile, which would just cover a small area. But that is a good question. I will look into it more in my data.
Awesome. Okay, so the next question is for Ashley and Tim. Do you see any potential for thermosiphons like the ground cooling technologies there, at least in vulnerable spots close to water bodies, etc.? There's some good results for passive thermosiphons which require minimum maintenance. Thank you.
I'll speak to this. So I'm not aware of any discussion about installing thermosiphons along the highway, other than the fact that some of the bridge pilings, and Tim, you can probably jump in here as well, but there are pilings that were left empty potentially for the installation of thermosiphons. And then actually there's a new construction at Gunny. A culvert is being turned into a smaller bridge further north towards Tuck, and they are building in the option for installing thermosiphons if it's needed in the future. So currently there are no thermosiphons along the highway. And for, I guess, the general here, I can kind of explain thermosiphons. They're not my background. I know there's Ed Grosek, a panelist, who might be able to provide a nice written up, but essentially a thermosiphon is a hollow container, or it's a container with some sort of fluid in it. And so in the wintertime, you can, hopefully I get this right, but in the wintertime, you can keep it open so that cold air can go in and push out hot air from deeper in the ground, hopefully cooling temperatures at depth, and extracting that hot air. And in the summertime, you'd close it so that that hot air doesn't get into the deeper parts of the ground. So it's one way of passively, or in some cases, we'll actively input cold air and pull out hot air to try to actually cool the ground or keep it colder during the summer hotter seasons. So it's an option that's been built in for parts of the highway. And then in town, I know there's been discussion of actually having to install thermosiphons or activate thermosiphons that have been installed on buildings, ARI being one of those buildings. And maybe Alice, you know a bit more about that. But yeah, sorry, Elizabeth, yeah, they haven't actually, I don't believe there's anything active right now, at least for thermosiphons. And then Ed, I'll just read what he wrote here. So he said all 8 ITH bridges have access tubes for future installation of thermosiphons if required. So yeah, I guess it's something that people are thinking about as we see warming temperatures in this environment. And it's nice as being built into built into construction practices now, so you don't have to go back and redisturb terrain. Thanks, Elizabeth. Yeah.
Awesome. Okay. If there's no more questions, I'm going to put in a quick plug. I'm going to thank our panelists here, our researchers, for their hard work. We want to hear more about your results as the highway ages, as your research gets more and more years of data on data on data. So that's really exciting. And we just thank you so much for the insight today. Our next talk, I'm just going to go ahead and share my screen. I want to share this one. Our next talk is definitely not local. We have a speaker coming to us from the university, from Western University. So he is part of the Canadian Astronomical Society, and normally we would have had an astronaut or a space scientist travel to the Beaufort Delta region to speak to schools. This year we're going virtual, and we have a professor of astronomy, Stanimir Metchev. He's going to talk about weather on other worlds, things like rains of molten iron and sand and salt. So it's going to be very cool. Classes who participate are going to be able to do some live Q&A with him as a follow-up. But yeah, mark your calendars, follow us on Facebook, and watch for those registration links. So thank you all very much for joining us today, and we have a great week, everyone. Bye.
Thanks. Bye.